Welcome to this series on artificial intelligence and machine learning. We're going to start from the very beginning and build up your understanding step by step. No math degree required. No coding experience needed. By the end of this series, you'll understand how AI actually works, from the simplest building blocks all the way to the large language models like ChatGPT and Claude. Let's start with the big picture. You've heard the terms artificial intelligence, machine learning, and deep learning thrown around, sometimes as if they mean the same thing. But they're actually different things that fit inside each other, like Russian nesting dolls. Artificial intelligence is the broadest idea. It means any computer program that can do something we'd normally need human smarts for, like recognizing a face or understanding speech. Machine learning is a smaller circle inside AI. Instead of a programmer writing exact rules, we give the computer lots of examples and let it figure out the patterns on its own. Show it 10,000 photos of cats and dogs, and it learns to tell them apart. Deep learning is an even smaller circle inside machine learning. It uses something called neural networks with many layers. It's what powers most of the AI breakthroughs you hear about today. Now let's zoom into the building block of all neural networks, the artificial neuron. Think of it as a tiny decision maker. Here's how it works. It takes in some numbers. These are the inputs. Maybe it's the brightness of pixels, or the price of a house, or words in a sentence. Each input gets multiplied by a weight. Think of weights as volume knobs. A big weight means that input matters a lot. A small weight means it doesn't matter much. Then we add something called a bias. Think of bias as a starting point, like setting the thermostat to a baseline temperature before adjusting. We add up all the weighted inputs plus the bias. Finally, the result goes through an activation function, which is basically an on-off switch that decides whether this neuron should activate or stay quiet. That's the whole thing. Every AI system you've heard of, from ChatGPT to self-driving cars, is built from millions of these simple building blocks. Now, how does the computer actually learn? It needs a way to measure how wrong it is. That's what a loss function does. Imagine you're learning to throw darts. After each throw, you measure how far your dart landed from the bullseye. That distance is your loss. A big number means you're way off. A small number means you're close. The entire goal of training an AI model is simple: make this number as small as possible. The computer makes a prediction, checks how wrong it was, and then tries to do better next time. That's the whole idea. So how do we actually make the loss smaller? This is where gradient descent comes in. Imagine you're blindfolded, standing on a hilly landscape, and you need to find the lowest valley. What would you do? You'd feel the ground around your feet, figure out which direction slopes downhill, and take a careful step that way. Then you'd feel around again and take another step. That's gradient descent. The gradient tells you which direction is downhill, and the model takes a small step in that direction by adjusting its weights. How big are the steps? That's controlled by something called the learning rate. If your steps are too big, you might overshoot the valley and bounce around. If your steps are too tiny, it takes forever to get anywhere. Finding the right learning rate is one of the most important decisions in training AI. But in a network with millions of weights, how do we know which ones to adjust and by how much? This is where backpropagation comes in. Think of it like grading a group project. If the final answer is wrong, the teacher doesn't just say the whole team failed. The teacher traces back through each person's contribution to figure out who made the mistake and how much they need to improve. Backpropagation does the same thing. It takes the error at the output and works backward through the network, layer by layer, calculating how much each weight contributed to the mistake. Then gradient descent nudges those weights in the right direction. The name literally means propagating the error backward through the network. This simple idea, invented in the 1980s, is still the foundation of how every neural network learns today. Let's put it all together into the training loop. It's beautifully simple. Step 1: feed your data through the network. This is called the forward pass. The data goes in, flows through the weights and activations, and a prediction comes out. Step 2: Compare that prediction to the correct answer using the loss function. How wrong were we? Step 3. Run backpropagation to figure out which weights to blame. Step 4. Use gradient descent to adjust those weights a tiny bit in the right direction. Now repeat. Thousands of times. Millions of times. Each complete pass through your training data is called an epoch. And instead of feeding all the data at once, we process it in smaller groups called batches, which makes training faster and more stable. That's the training loop. Forward, measure, backward, adjust. Repeat until the model is good enough. One last but important concept: overfitting. Imagine a student who memorizes every single answer in the textbook, word for word. They'd ace a test with the exact same questions. But give them a new problem they've never seen, and they're lost. They memorized instead of understanding. That's overfitting. The model performs amazingly on the training data, but fails on new, unseen data. It memorized the noise instead of learning the real patterns. To prevent this, we split our data. We train on one part and test on another part the model has never seen. If performance is great on training data but terrible on test data, we know the model is overfitting. There are techniques to fix this, using more data, making the model simpler, or adding something called regularization, which is basically telling the model not to rely too heavily on any single weight. And that's the foundation. Everything we'll cover in the next 6 videos builds on these concepts. Next up, neural networks.